Hello, good morning. Today I am going to explain viscous dissipation between parallel plates. So here the problem statement is, suppose there is Newtonian fluid between two flat parallel plates, b distance apart. The upper plate is moving at a constant velocity v and bottom plate is stationary, this one. The temperature at top and bottom plates are Tb and T0 respectively. So here the coordinate systems are chosen as the base plate. Here x-axis is taken in the direction of the flow, y-axis in the perpendicular directions, and z is, you can say, this perpendicular to this page. Now considering for fluid properties constant with respect to temperatures, now applying your x momentum balance. So your x momentum balance is this, that del u upon del t, u del u upon del x plus v, del u upon del y plus w del u upon del z equal to rho gx minus del p upon del x plus mu del square u upon del x square plus del square u upon del y square plus del square u upon del z square. Now we are putting our conditions from our problems. We are solving it for steady state, so nothing is function of time. This derivative is getting cancelled. Fully developed flow in x directions, so del u upon del x is 0. Flow is purely one dimensional in x, so v and w are 0, so these two terms are getting cancelled. Gx is 0 because g is acting downwards, so gx is 0. No applied pressure gradients, so del p upon del x is also 0. Del u upon del x is 0 from fully developed flow. Del u upon del z, so this z dimension is excessively large as compared to the y, so therefore del u upon del z square term would be much more lower than del square u upon del y square, therefore we are neglecting this. So finally we are ending up with 0 equal to mu d square u upon dy square, where u is the only function of velocity. From here you will calculate your integrate it, your c1, integrate it one more time. Your boundary conditions are at y equal to 0, u is 0, y equal to v, u is v, because the top plate is moving with a constant velocity v. By substituting that, your C2 is coming 0, C1 is coming C1b, so C1 is v upon v, so your u is v upon v multiplied by y. Now applying equation of change in x, y, z directions, so this is energy equations. Now we are putting constraint from our problems, so steady state, so this term is getting cancelled. Thermally developed flow, so temperature gradient is also not there in x direction, so del t upon del x is also 0. Purely one dimensional flow in x, so vy and vz is also 0. Then thermally developed, so del t upon del x is 0. No conduction in z direction, so therefore del t upon del z term is also 0. We are considering the conduction only in y direction only. Now this term is viscous dissipation here, so we left with two terms, 0 equal to k del square t plus phi into mu into phi b. Phi b is viscous dissipation, which is given by this one actually function. So now here in this also we are putting our own constraint. Fully developed flow in x direction, so del p x upon del x is 0. Now v is not V is 0, no velocity in the y direction, no velocity in z direction, so these two terms is also 0. So Vy is 0, so this is 0. Vz is 0, this term is also 0. Now this is also 0. Now one-dimensional flow only in x direction, so velocity is not changing with respect to z, because z boundary is very large as compared to y. So from here you are this Vz is also 0, then Vx upon del Vx is 0, fully developed flow in x directions. Now Vy is already 0, Vz is already 0. So from here, if you will say that we have left with only one term, phi b equal to del Vx upon del y. So v is only a function of y only, so partial would be converted to total. So dbx upon dy square, so you have this expression v upon b square. So from here now we can use equation 3 and 4. 0 equal to k d square t upon dy square plus mu v upon b square. So V upon B is gamma dot, is shear rate. So this we can solve it here. So finally from here T equal to minus mu upon K gamma dot square y square upon 2 C1 by plus C2. Now boundary conditions are at y equal to 0, t equal to t0 so from here we can get your C2 equal to T naught. At y equal to B, that upper plate, bottom plate, y equal to B, temperature is TB actually. So for that case, TB equal to minus mu upon k gamma dot square b square upon 2 plus c1b plus c2. So from here we can calculate the expression of c1. Now substituting expression of c1 there from equation 5, 6 and 7. So your expression for t is coming from here. So that t minus t naught equal to tb minus t naught y upon b plus mu upon 2k gamma dot square plus v square bracket y upon v minus y square upon v. Now arranging this here, so we are getting t minus t naught upon tb minus t naught equal to y upon b plus gamma dot square mu b square upon 2k tb minus t naught y upon v minus y square upon v square. So here this particular term is known as Brinkman number. So that Brinkman number is mu gamma dot square v square upon k tb minus t naught, and this you can substitute here. So Brinkman number is practically, if you say that rate of energy, this is rate of energy generation actually due to viscous dissipation divided by rate of conduction. Now these are some various dimensionless parameters in heat transfer, that Re Reynolds number, then Faraday number V square upon Gd, Prandtl number Cp mu by K, momentum diffusivity upon thermal diffusivity. Brinkman number we have derived in this only just now, that mu v square upon k t naught minus t, the rate of energy generated by viscous dissipation upon rate of heat conduction. Nusselt number Sd upon k, convection heat transfer upon conduction heat transfer. Then Grashof number is given by this rho square g beta t naught minus t1 dq upon mu square. Pecklet number, Prandtl number into the Reynolds number Vd upon alpha. The ratio of Grashof number and Reynolds number square is given by this buoyancy stresses upon inertial stresses. Then Pecklet number is also given by this, the rate of heat transfer due to convection upon rate of heat transfer due to conductions. So reference for this actually is transport phenomena by Bird, Stewart and Lightfoot. So thank you very much for your interest. In case of any doubt, you can leave your comments, and thank you very much.